Good morning. How are you today? I'm from the Barcelona Supercomputing Center. I'm here as a member of the scientific committee representing the ACM. So I will be chairing this session until the coffee break. So we start with a Spark session, and you know how these sessions work, and we have a moderator that for now you know very well, Tom Crawford. Thank you.
Okay, third and final Spark session. We hopefully know how these work at this point. There will be 15 minutes per speaker. There may or may not be questions. And we have 5 speakers for you today. But before we get to that, I don't actually have to do anything today because we have an incredible opening for the day's proceedings, which is going to be a reading of a poem from one of the young researchers, which has been written during the week so far in Heidelberg. And this will be from Joshua Hussaini, who is originally from Nigeria and is currently studying for his PhD in India at the University of Kerala. And he will be reading his poem entitled At Sunrise in Heidelberg, which is dedicated to everyone at the HLF. So Joshua, please come to the stage.
In Heidelberg's embrace, where the Neckar flows, a dawn unfolds gently as the light starts to pause. Between Oden's great forest, in valleys so tight, the city awakens a canvas of light. The sky, a vast function, in colors it glows as clouds catch the gradients in pinks, reds, and rose. On the ground, the coordinates begin to align, a convergence of minds where math and computer science entwine. 200 exceptional young researchers from all over the world, exceptional thinkers in mathematics and computer science is vast terrain, in rows and in columns, like matrices form, in the hall of great fame, where ideas are warm. Ready for the 12th Heidelberg Laureate Forum, a week to explore, to network and share, to unlock every door. In a space designed for exchange of ideas, where concepts collide, they will meet the great with knowledge as their guide. Fields medalists speak of conjectures and proofs. Turing Award winners share algorithms' truth. Abel Prize holders with elegance and grace. I am you, Abacus medalist, Nevanlinna's pride. In the realm of equations, where insights abide, in this mathematical heaven, they all find their place. With axioms and postulates, they will challenge the norms, exploring the realms where new ideas swim. From fractals to functions, from sets to theorems, in the language of numbers, they will craft their own dreams. Grateful and eager, these young minds convene for a week of discovery where logic is keen. So here is the 200th, the bright and the bold, at the 12th Heidelberg Laureate Forum. Let theorems and algorithms unfold. With cheers and with laughter, let the journey begin. In the heart of this great city, where math and computers wonders spin.
I will not be reading a poem. That was fantastic, Joshua. Okay, so on to the talks. So our first speaker this morning is Pat Hanrahan, who of course is possibly well known to many of us, working in computer graphics, creating images, animations for films, video games, But Pat also told me that as part of this role, he had to demo the software to various people throughout his career. And some sort of highlights were a demo for the German electro-pop group Kraftwerk, a demo for Jerry Garcia, the guitarist from the Grateful Dead, and also a demo for Robin Williams, which is quite fantastic. Pat was awarded the 2019 Turing Award, and today we'll be talking on the languages of mathematics and computing. Pat.
Okay, good morning, everyone. I hope you had a good time yesterday, and I'm really glad you were able to wake up this morning. I just barely made it myself, but okay, so I actually have a slightly different talk. So I work in computer graphics, but I was thinking of a talk that might be sort of a little different, it might be interest of the broader audience of mathematicians, computer science. So I called it The Languages of Math in CS. And so what I do, basically, I'm a programmer. Okay, I take ideas and build systems that implement those ideas. Okay, and I like to program. I still program every day. You know, I'm really upset I haven't been able to program the last few days. So, but anyways, I program a lot. And what I usually do when I write these programs is I build like little languages, like what we sometimes call domain-specific languages. So I think the reason I have this Turing Award is because when at Pixar, I developed this thing called a shading language or a shader that eventually became the shaders of GPUs. Okay, and this shader is how we make a picture. So this was actually a picture that I used to use as a test image at Pixar when I worked there many, many years ago. And it's this corroded teapot. And the way this system basically works is it takes the teapot and it breaks it into what we call micropolygons, which are really itty-bitty little polygons, roughly 1 pixel in size. And then for every one of those little itty-bitty polygons, it runs this program. And you see there's various information, which I put in red sometimes, P and N. So P is the position on the surface, and N is the normal to the surface. And the first thing it's doing is it's actually it's a smooth surface, so it's adding some bumps to it by adding up some noise. Okay, so that's like a fractal noise pattern there. So it gets this variable turb, which is like a bunch of noise added up at different frequencies. And then what it does is you see it displaces the surface P by some amount in the direction of the normal. And then once this surface gets displaced, the normal changes because different regions are moving at different amounts. And then when it does, it actually computes the color. So the color I is the color that you would see if an incident ray hit the thing. So I like to build these little languages. And and what happens in all these languages I've built is there's a bunch of mathematics in them. So in the case of this particular language, there's a little knowledge about like differential geometry. Like what you do is you're actually that little polygon, we think of that like a little differential patch, okay? And if you know about differential geometry, you have this little local coordinate frame at every point on the surface. And it has a position, and it has these tangent vectors, you have some parameterization, U and V, and so it has this information. So embedded in this language and the system is a little bit of differential geometry, a lot of math of vectors, and so on, okay? So that's a typical thing I do. Here's another language I built a few years ago, which became the basis of Tableau. And so what this was sort of like SQL. So some of you, if you computer science, probably know SQL, but this is like a graphical version of SQL. So this is an older picture, but this is a map of New York City, and this was the election when Barack Obama was running against John McCain, and this shows you how much money every zip code in New York gave to each of these candidates, okay? And, so this thing, you can sort of figure this out, and I'm not going to spend a lot of time on describing exactly how it works, but, databases are based on relations and relational algebra. So this language sort of has the semantics of the math of relations. And so again, you have some underlying math, and you build this language that takes advantage of that math. And the reason you use the math is because that gives you like expressions, right? You can form expressions with geometry, you can form expressions with relations, and so you can get this powerful compositional system. So that's how I generally tackle problems, embed math. Now, recently I gave a talk at the International Conference on Functional Programming Languages, and they just asked me to talk about how I like to build languages. And I told him, well, sort of what I like to do is actually nowadays is take an existing language and enhance it, which is called an embedded computing language. And then, what you normally do is you define a bunch of new types and a bunch of operations on those types, and then, you're off and running. But I was telling him, I'm having these problems. At the time, I was working on a tensor processing language, right? Everybody does machine learning. And I have to make these tensors like I, J, K of floats. So there's this three-dimensional tensor. And I have trouble making these things. Now, some of you may know this, even in languages like C, you can't really say array of n and float, okay? You can, an array is just a pointer to a memory location, the first float. There's no notion of the length of the array in the type system. So as a result, if you can't type check this, you can't test whether when you index the array that you're not going out of bounds. And of course, that causes all sorts of problems because that would be an illegal access. Or if you write out of bounds, that's a really bad thing, okay? So that's not part of the type system of the language. I even showed another example. You might like to write some expression which concatenates two arrays or two vectors and makes a vector of length m plus n. And you'd like to guarantee that your function actually produces a vector of length m plus n. So, so I was just telling them and said, well, we know how to solve that problem. And they said, yeah, you should be using what's called a dependently typed programming language. And they said, yeah. And I said, what's that? I said, well, it's a really simple thing. It's where all the types can depend on values. So I don't know how many people know about dependently typed programming languages? A few. Good. All right. Good. Few. Okay. Not many. I didn't know about them. Okay. So I decided, well, this sounds really great. I mean, this just seems so elegant, right? Why don't we just have all our types that depend on values? So I started looking into it. And then I find out that the languages that use dependent types are like Khot and Lean. We've talked about Lean a lot at this conference. They're theorem provers. They're fair. So that's sort of interesting. These theorem provers seem to use these dependent types. Okay, so I want to explain this because I think it shows a deep relationship between computing and mathematics. So here's a language. Okay, so I tend to use Agda, and that's because it's really a programming language which has been enhanced to have dependent types, because I'm a programmer. I don't want a proof assistant. I mean, I'd be happy, not against proof assistant, but I want a language I can use dependent types in, right? Sounds like a great idea. So this is in this language. So here we're defining a set of natural numbers, n, and we're using this piano numbers, but I tried to pick a mathematical way of doing this because I hope everybody in math knows about this. But you have 0, and then you have this successor function, which is like 1 plus a number. So if you have just those two things, you can make all the natural numbers. And so 1 is just successor of 0, 2 is just the successor of 1. And notice that this natural numbers is a set. So when we think of types, we usually think that they're sets, okay? So the set of natural numbers. And this is what's called an algebraic data type, where there's two ways of making a set, and it's recursive. In other words, a set is defined in terms of itself. So a little tricky. That's a whole subject in itself, but it should be pretty intuitive, right? So when we say x's of type natural numbers, we're really saying x is a member of that set. So that's what we mean by that, okay? So you write this program and you try to run it, and the type checker checks that the function 1 constructs a natural number legally, right? Like you could do it using some other function besides 0 and successor, and it will complain. It says, that doesn't type check, right? Doesn't type check, it's gonna complain. It only wants you to do legal things. In other words, you only can operate on certain things in certain ways, okay? But there's another way of thinking about what this program is doing, is the function 1 demonstrates that n exists, right? Because I made an n, therefore there has to be a set n. In fact, and you can interpret this as the existence can be interpreted as a proof of n. Now, you probably want to mull, if you haven't ever heard that, you'll probably want to mull that over a lot in the next few weeks, okay? And if the function type checks, the proof is valid. That's it. Okay, done. All right, anyway. But anyways, that's how it works. It's not, and so everybody that's using a a language with a type system that's sound is running a proof checker every time they compile their program. And so it's not like some exotic thing that only math people do in Lean, okay? Okay, now, but here's where it gets interesting. You can form new types. So, and I'm given to condense a whole chorus, okay? But, there's a new kind of type called a product type, which would be like the tuple type in Python or the struct in C, which you take a record with 2 fields, say. So the way we'd write that is there's this type product which takes 2 types, P and Q. They can be any types and forms a product of P and Q. And there's this operator, which is this comma, which is like the Python tuple operator, that takes a P and takes a Q and produces a product of PQ. So here's a function, takes a P and a Q and a product. So this notation where you have these arrows like that is just a way of writing functions in these languages. So they use currying. And then that thing where they put the little underscores on both sides means you've just extended the syntax so the comma acts like an infix operator. So you can, just show you what these fix. Anyways, okay, so that's simple. We all do this. We take the product, we form structs. But you can interpret this as a proof of and. Because if you have something P, if you have a value of type P, that's a proof that P is true. And if you have a value of type Q, Q can be interpreted as a proof that Q is true. And if you have a proof that if P is true and Q is true, then P and Q is true. That's how the mathematicians would write it. This is how we would write it. So in language, in computer science, and is equal to product. And okay, so now there's other axioms. Oh my God, slides got goofed up here. Okay, I don't know what happened there, but you also have these, other axioms which are like the reverse. If P and Q is true, then P is true, and if P and Q is true, Q is true. So if we add some functions like first and second, which returns the first of this product and the second of this product, okay, we can write the theorem that P and Q, and of P and Q is equal to and of Q and P. And you just do that by writing a program that takes an and of P and Q and returns an and of Q and P. And if that type checks, you have a proof that that's true. Is that cool? Okay, and so this, and then you can have this other type called sum, which I'm not going to go through the details here, but sum is like union in C, or either in Haskell, or optional maybe in C++. But you can either have a P or a Q. So if I'm giving you a P, I can make it a sum. If I give you a Q, I can make a sum. But or is just sum. So, and it's because if you have a P, you have a proof of P and Q, or P or Q, and so on. And even more simple, implication. P implies Q. What's P imply Q? P is just a function that if I have a proof of P, then we can create a proof of Q. Because if P is true, then Q has to be true. So I have to write a program, transforms P into Q. And if I have such a program and it type checks, I have implication. Okay, isn't that cool? Okay, anyways, there's this famous theorem, which we used to all be taught, called the Curry-Howard isomorphism. How many people have heard of that? Wow, we're not doing a very good job. Okay. By the way, I never took any computer science courses. I know this. Okay. Okay. Anyways, this isomorphism says if you have propositional logic, there's these various things that you all recognize as mathematicians. But then in computer science, we have these other things, which are types. And I've shown you how I can construct all these. I haven't gone through a few things. I haven't told you about true and false and so on. But there's an isomorphism. In other words, anything you can do with propositional logic, you can do with this type system and vice versa. And so it's like 2 languages. We have the language of mathematics and we have the language of computing. And they're sort of mirrors of each other. And it's sort of neat when you have 2 ways of thinking about the same problem. And that's what's cool about computing and math is they sort of are 2 ways of looking at a lot of problems. Okay, so that's cool. And so almost all languages have these types in them. And so all languages are equivalent to propositional logic. So if you want to do propositional logic in C, no problem. Okay. Now, propositional logic isn't that interesting. You want to do first order logic. What does that mean? That you need quantification. Remember that? You need to say for all x, something is true. Q of x is true. Well, Q's are types. So in order for that to be true, you have to be able to have a type that depends on a value. Because x is a value. It has to be true for all values x. So anyways, that's why you have dependently typed programming languages, because now you can embed first order logic, and once you have first order logic, then you can build up much more complicated proofs. And that's why all these dependently typed languages are used for theorem proving. Anyway, so I'd tell you about that. So I discovered that. Okay, now, so what you can do in these languages is prove things. So you can say, like, let's say we take our natural numbers and we define addition. So we're doing it by saying 0 plus n equals n, and 1 plus m, successor is like 1 plus n is equal to 1 plus m plus n. That's the definition, recursive definition. You peel off one of the ones, you put it from m and move it over to n, and you eventually, that recursion terminates and you get the value of the addition. Not the most efficient algorithm, but suppose we wanted to implement this one to prove that it's commutative, that for all m and n, m plus n equals n plus m. That'd be useful. Like, did I implement this? Is this a good definition of addition? Okay, so I fired up ChatGPT the other day, typed in my slide, given the Agda program this, it says to me, great question. You want to prove the commutativity of addition on piano numbers in Agda. And then it writes out the math. That's nice. Okay, cool. Then it says, all right, well, I haven't told you about this, exactly what this equality thing is. Sorry, don't have much time, already over time. Anyways, it says, I need this equality thing, which is just a relation in some sense. And it's sort of like product. It's a little different. But anyways, it says, I'm going to generate this lemma. It's a pretty trivial lemma. And this follows immediately from the definition of plus. It's giving me a pretty good explanation, actually. And notice it's generating code that I can just run, and I can test the code. I can run the code, and if it compiles, that's true. So I can verify it's true. And then it says, oh, let me prove it. And then here's the proof. And I don't have time to go into the proof. I hope a bunch of you come up and ask me in the next day or two to explain this proof. But there's basically two cases. It says, suppose m is a 0, which is one of the natural numbers, then it's a trivial proof. But suppose n is the successor of another one, it proves it by induction. So anyways, I don't have time to go through it, but it just does it. So anyways, it says, I did it one way, do you want me to do it another way? Anyway, cool. So, all right, so isn't this cool? All right, so if you use Agda, and I've been using Agda almost every day now for writing programs, there's this huge library of these mathematical objects that I can just use in my programs. So, I happened to be doing something with tensors, and I needed this thing, which was like a semi-ring, and I figured out it was a semi-ring, and I looked up in the Agda library, and I see this. And it's just like a class. It says, if you implement this class, you're a semi-ring. In order to implement this class, first of all, you have to give me a set. You have to give me two operators, plus and times. Okay, you have to give me these identity elements, E. So for the natural numbers, the identity is 0 for plus, and the identity is 1 for times. And then you have to provide all these proofs. Because if you go look in the math book on what a semi-ring is, it says it has to have all these properties. So if you have all these properties, then you're a semi-ring. So, well, that's sort of cool. I mean, people were saying, shouldn't be able to read lean. Is that hard to read? I can't imagine anything easier to read, okay? Anyways, so, I can just, but I don't have to go and look at all the proofs, but if the person provides this library, all these proofs are there. They're there for me. And so what does that mean? That if I have these libraries that I can use of all these mathematical ideas, okay, I can use them in lots of good ways. So I can certify that my implementations are correct. That is, if somebody says it's a semi-ring, they better prove it's a semi-ring. I'm guaranteed that it will be. And I can build new libraries based on those libraries and use all those proofs to build new proofs. So now I'm making better software is provably correct, is easier. Then you have all these abstractions built in. So like when I was building this tensor library, there's a abstract definition of a tensor in there. And I can actually make sure I implement it right. Okay, I know what I need to do to implement it right. And so I can make a subclass sort of like of tensor, of this abstract tensor and a real tensor. And then really cool is like I want to rewrite my program. I want to change it in some way, refactor it. I can use those rules, those theorems. If I have A plus B and I want to replace it with B plus A, I know that the implementation will give you the same answer because they prove that those two things are equal. And if I'm writing a compiler, which I do all the time, compilers, what they do is they take programs and rewrite them into other programs, and they look for the most efficient implementation of the program. And so I can search over these different rewrites, and now I can implement a compiler. So if I want to make a GPU version of it, I can do that. So that's awesome. So I want all this math, okay, that's in this forum. But what's interesting, it's been very interesting to watch what's happening in these communities. So in EGDA, they're trying to build this library of all mathematical knowledge, just like they are in Lean. They're motivated by the same reason that Lean is. But they're having trouble with it because when you go read a book on math, people often think of math differently from one book to another book. So what happens is like one guy wants to think of all math as being derived from category theory. So they implement the library as if all math is derived from category theory. Another person just says, I want to make a group. He writes a group, but the group library doesn't interoperate with the category theory library. So they have to agree on how to think about all of math and how it's related. And that's like a software engineering problem. That's what we're good at. Also, the ergonomics is not very good. Okay, I'm all over time, but anyway, I'm excited about the subject. Anyway, so also what's cool, and that's really the reason for the talk, is there's two languages we're talking about here. The language of mathematics and the language of programming. So this is the way I characterize them. You can argue with me after my talk, not in question. But math is incredibly ambiguous, and it's not standardized, but it's very flexible. That's how I'm going to characterize it. Computer languages are very precise. In other words, the compiler has to accept them, has to be clear what they mean. They're sort of powerful, and they introduce all these concepts that help remove ambiguity from mathematical notation, like variable scoping. That's just as an example. But they can tend to be cumbersome and not very flexible. But people are trying to make them more flexible. But they are executable, too. So when I take my math and I do it in this language, then when I'm done with my math, not only do I have all these theorems, but I can run it. So if I have a new machine learning algorithm, I can implement it, prove all the theorems about it, and then run it on a real data set, maybe do something useful. So I think that we're in a very exciting time where we can invent notational systems that take the best of math and the best of computing, and we can build systems that are more robust from the computing side and interesting from the mathematical side. And I think computer scientists and mathematicians should be working together to really make this stuff practical in the next, say, 5 or 10 years. Thank you very much.
Okay, so next up, we have Martin Hellman. Now, Martin, of course, is well known for his work in cryptography, but did you also know that he has 2,700 hours experience flying, and not just as a passenger, as a pilot? So Martin was telling me that he frequently flies a motor glider, which is a glider with an engine to allow it to take off. So a standard glider would be towed and then released, but the one that Martin likes to fly has its own engine for takeoff. And today, he will be talking on graphs in cryptography. So, Martin, the stage is yours.
Thank you. So, by the way, I don't fly anymore, which is why I'm alive. I sold my motor glider 15 years ago. Let's see, so this is, yeah. Okay, thanks. Well, thank you. So I'm going to talk about graphs in cryptography, and let's see. Many of you know about the Advanced Encryption Standard, which, by the way, was designed in Belgium, and that has 128-bit block size and a key sizes of at least 128 bits. The data encryption standard, which was promulgated roughly 25 years earlier, is something that many fewer of you know of, although the oldsters among us do. It has a 64-bit block size and a 56-bit key size. Now, 2 to the 56th is roughly 100,000 million keys, so DES can be broken by an exhaustive search. That was a surprise, at least to me. And Whit and I realized this. In 1976, Whit, Diffie, and I estimated, oh, and by the way, you see the links here? The PowerPoint deck, which is available to all of you, has the links in it. So Whit, Diffie, and I estimated that a special purpose chip could search 1 million keys per second. And so you wouldn't just buy one of these chips, you'd buy 1 million of them. You're then searching 1 million keys per second. And how long does it take to search 100,000 million keys? 100,000 seconds, which is about a day. We estimated that the cost was roughly $10,000 US per solution. Well, exhaustive search was expensive but doable, but even better would have been a time-memory trade-off. A pure time-memory trade-off, if it existed, cryptanalysis would have been trivial. For example, we could let t equal m, time equal memory equal 2 to the 28th, which is the square root of 256, so the product is 2 to the 56th. That would take 256 megawords of memory and 256 million operations. We had been trying to find a time-memory trade-off for several years when the solution came to me when I was hosting Adi Shamir, and a lot of you may not know who Adi Shamir is. He's the S of RSA, and that's Ron Rivest, Adi Shamir, and Len Adelman. So this was at the faculty club. We were standing in line, and I'd been trying to do this for a long time, and it just came to me how to do it. And my time-memory trade-off, and that link is to the paper that you can read, was based on the birthday problem. In fact, half the problems in cryptography that have nice solutions are solved by the birthday problem. It only takes 23 people in a room before there's more than a 50% probability of overlap. And that's because if there are n days in the year, it only takes about square root of n people. The square root of 365 is 19.1, which is very close to 23. With k people in the room, the reason for this is each pair of people has only 1 over n chance of overlap, but there are k choose 2 pairs of people, so the expected number of overlaps is roughly a half when k is equal to the square root of n. And so this picture shows how we use this. P0 is something like 8 ASCII spaces, and it's put into DES, and the ciphertext comes out when the key is K. And then we have a reduction function, R, at the bottom, which takes 64 bits and maps it to 56 bits, any which way you want. It doesn't matter. And then you loop that back in the key port. Computing f of k from k is equivalent to enciphering, because the only extra thing you have to do is a reduction function, which is very quick, while computing k from f of k is cryptanalysis. And so this picture shows how if you have starting point 1, a key, and you compute f of it, you get x11, and you do this t time units until you get x1t, you call that ending point 1, EP1. And you do this for m possible starting points. Once you've done this, you can find any key that's in the matrix. Let's see, no, I want to go back. Once this matrix is computed, it only takes m words of memory, because starting point 1, ending point 1 is all you need to find anybody in the first row. And what you do is you start with the key that you're trying to find, you get f of k, and you keep iterating until you've done it t times. If you've hit an ending point, then you know where in the matrix it is, and you can find it. So the problem was The problem was that if you let t equal m equal the square root of n, which is 2 to the 28th for the data encryption standard, a random graph would have significant overlap, and so you wouldn't cover all the points. And the solution that came to me in the at the faculty club waiting with Adi Shamir to be seated was to let m equal t equal n to the 1/3 power, because now you've only got n to the 2/3 points in the matrix, and there's very little overlap, and so you now have n to the minus 1/3 chance of success, but there's almost no overlap. So you do this now, this is the key thing, you do this for roughly n to the 1/3 different reduction functions. And that was the key result. And this requires roughly n to the 2/3 in time and memory after a pre-computation, which is equivalent to an exhaustive search. So this is also the genesis of rainbow tables. So I'm going to leave time memory trade-offs and run to the distribution of drainage. And what the hell is that? Well, we tried to find statistical irregularities in DES because they might allow cryptanalysis. When Justin Rainieri was my doctoral student, he was a very good hardware guy. We had a board that had a DES chip that he interfaced to a PDP-11 mini computer. This was in a microcomputer, actually. And we did this because DES is very fast in hardware, very slow in software. So having a hardware implementation really allowed us to do a lot more. But we were surprised when the drainage of the first experiment that we tried was estimated to be at least 99%. We thought this was a statistical irregularity. But analysis showed that the probability of our result was roughly 9%. So it was surprising, but not very surprising. And we did a lot more. So let me define drainage. Here is a graph, and you see the rivers and the lakes. The lakes are the circles, and then some keys drain into lakes. And the drainage of the above graph is 8/13 because it has two components. The large component is size 8, and the small component is size 5. So if you start with a random key, it will drain with probability 8/13 into the largest component. And we found that our largest component was actually 99%. And that's because when we did theoretical analysis, we found that the distribution of drainage looked like this. It peaks very close to 100%. And so that was very surprising. Well, let me leave the cryptography and turn to a problem that was posed to me by my grandson-in-law, who's here, Jake Woods. He posed it to me as a brain teaser, and this was kind of fun. You have 100 prisoners have been condemned to death, but and there is a link to a description of this problem, but the warden offers to reduce their sentences, commute their sentences, if they can accomplish the following task. He numbers the prisoners from 1 to 100, and he puts 100 pieces of paper in 100 safe deposit boxes, and he lets each prisoner, the prisoners can talk among themselves ahead of time, but once they start opening boxes, they can't do that. And so it seemed to me that the answer was 1/2 to the 100th power, because the first prisoner only has probability 1/2 of finding his number, and all 100 prisoners have to find their number to have their prison sentences commuted. Okay. So this is the picture from the Wikipedia of the prisoner trying to find his number. And the reason that it turns out the probability is 31% rather than 1/2 to the 100th power, which is essentially 0, has to do. Sorry, I didn't. Yeah. So the solution is that prisoner I first opens box I, and if he finds his number, he stops. If not, he goes to box J, which is the piece of paper in box I. And this succeeds if the largest component of the associated graph is no larger than 50, which event has probability 31%. And I'll be finished in just about 30 seconds. The reason that this was so different from the time memory trade-off is that here the function is 1-to-1, not many-to-1. So the graph has only lakes with no streams and rivers feeding them. It looks like this, and the probability of the biggest component being no bigger than 50 when you have 100 random points in a random graph is 31%. So I will stop there, and that is the talk. Oh, and thank you, Jake, for the problem as well as for helping me up and down the stage.
Thank you, Martin. Okay, now our third speaker of the morning is Torsten Hoefler. And I noticed when looking at the schedule that this is our third speaker in a row on Thursday morning with a surname beginning with H. So naturally, I wanted to compute the probability of this occurring. This is how my brain works. I'm sorry. I'm sure there are many other people in the room whose brain work in the same way. So I'll give you the quick rundown. We have 190 laureates. 13 of them have a surname beginning with H. So if we assume a uniform distribution of them speaking and we sample without replacement, it's about 1 in 4,000. So here to give a 1 in 4,000 talk is Torsten Hoefler, who was awarded the 2024 ACM Prize in Computing, and today we'll talk on the computational pathway towards artificial human-like intelligence. Thank you.
Thank you, thank you. So talking about unlikely events. Yeah, exactly. Talking about unlikely events, about 10 years ago, one of my lab members asked me to write a recommendation letter for her to come to this forum. And she went here, she was admitted, Sabela Ramos was her name, she's now in the Gemini team, by the way. When she came back, I asked her, how was it? And her eyes were fiery and like truly inspired. And to be honest, I was a little bit jealous. And it's just like, well, you know, now you're too old to ever make it to this forum, and here I stand. So I'm incredibly thankful for the organization of this forum. I'm also incredibly thankful for my community, the HPC community, for the support over the years. And I'm an HPC guy, so I'm an engineer. I'm a performance engineer. I make things fast. Big things go fast, very much like Jack Dongara. Not so much math, because in the area where I'm working, there is unfortunately not enough math yet to explain the phenomena we are seeing. But I hope this will come. So I choose this catchy title, The Computational Path Towards Human-like Intelligence, just to make you come. I didn't know you were automatically coming, so next time I'll choose a less catchy title. But really, it's the reasoning model is all you need, I would say, but then on the right machines. I want to connect back to earlier this week. So Sanjeev was giving a very deep talk on super mathematicians, to some sense. And he says this math superintelligence doesn't mean it's perfect, it's just that it's better than humans. The reason that it's getting better is because it's tireless. It keeps repeating the self-improvement loop getting better. That's the magic. I would just say, yes, this is magic, but we can explain every single bit that is calculated, every single bit that moves. It's all computation underlying. It's just that the combination of these things are seeming like magic because we can't explain them yet. So I challenge all of you, all of us, to solve that together, to demystify this whole thing. And then later, by the way, this is a big benefit being at the end of the session. and then later, David Silver said something very profound. Learning from experience is extracting knowledge from the things it does in its environment. If we do this, we transform the future of AI and thereby humanity. So a very bold statement. So we are here to transform the future of humanity. Great, great, great. So let's go back to last week, OpenAI releasing this plot. This is a math benchmark, AMI, one of the not so many math benchmarks that hasn't been solved, essentially. And you can see a lin log scale. So the linear scale is on the past accuracy, so that's how many problems do I actually solve with the language model. And then the log scale is the test time compute scale. So that's the amount of computation involved in solving the problem. And of course, it's a typical industry plot, so it doesn't really have a legend, so you don't know if it's hours or years or something like this. But it's the log scale. So what you see immediately is that for 1 or 4K more problems solved, I have to invest exponentially more time because it's a linear thing. Oh, that's scary, right? And now I would claim that computation today is the new oil because it's going to change humanity. It may become one of our most important resources, actually, if we think about it. And this is quite nice because I'm coming from a little country that's Switzerland. We don't have any resources. We have lots of mountains, but there's not much resource. But now we can have a supercomputer. And actually, this is somewhat democratizing, and anybody with the reasonable starting resources can have that. So this is great. I want to leave that as a message. And as we enter this age of computation, Like I have a much longer version of this talk that explains this in more detail, the vision. But I really believe that as humanity, we're entering this age of computation where we're using computation for pretty much everything, for producing, for doing all kinds of things. So we are at the right position. And this age of computation has multiple eras if you look at machine learning. So there was an era of model scaling where we built bigger and bigger and bigger models in 2017. Many of you probably still remember. But this kind of stopped because it turned out that bigger and bigger models are more expensive to serve, or more expensive to run, so it doesn't make any sense. We don't want this. We wanted smaller models, actually, because that's what, as small as possible. And then we went into this era of data scaling, where we fed more data into the models to make them smaller. And that was nice, because for high-performance computing people, there was even more compute we needed to train these models. So at the end, we always needed more compute. But then what happened is this happened. Basically, Ilya said, well, we're running out of internet. We have essentially run the whole internet through those models. So what are we doing now? Well, actually, David said it in a very nice way again. Human data is the fossil fuel of AI. I want to emphasize this. This is very, very fitting. Because fossil fuel brought us here, brought us where we are today. Without fossil fuel, we wouldn't have developed as fast as we developed. Without human-generated data, these language models wouldn't be where they are today. But we're running out of it. So we have to use it more efficiently, but we're running out of it, so we need an alternative form of energy. But what is this energy that we've been using, or this fossil fuel? This is great. We have generated models that are great at knowledge tasks. So many of you have seen this plot, probably. It's the GPT-4 plot. On the x-axis, we have various benchmarks. These are all knowledge benchmarks, very, very simple knowledge. Actually, not simple. I cannot answer most of those, but knowledge questions. And on the y-axis, you see the humans ranked from 0%, the worst human, to 100% the best human taking these tests. So the line is 50% of the humans. So it's basically the median human, or we could argue the average human, depending on the distribution. But you already see that this AI model, the single model, is better than the average human on most tasks. I would claim it's actually better than the best human on a large enough variety of tasks. So that's getting interesting. But this is a knowledge test. This is just looking up information. This is a gigantic database. So we managed to build a gigantic database that has a language interface that is better than any of us in answering knowledge questions. So we've been using this for a while. This is great in input-output prompting. So we ask the question, we get an answer. We ask the question, we get an answer. And we all know why it works. So we all know how it works. It's emulating the statistical distribution of language that it found on the internet. So it literally builds a database. But now, if you ask it a sufficiently different question from what it has seen on the internet, like this question, sort these numbers for a sufficiently large number of diverse numbers, this has not been on the internet, right? So now it cannot look this up in its database. And actually, the first models performed really badly at this. We were like, oh, great, math is safe. Our job is safe forever because we can do reasoning as humans. But now it turns out that chain of thought was discovered. And chain of thought is fundamentally surprising to me, to be honest. What this did is basically we give the model, instead of just the task, we give it a little description, like you explain to your child, well, to solve this problem, you would be doing X, Y, and Z. Like here's a smaller little example, and now you pose the problem to the model. And indeed, the model got significantly better, by a factor of 2 nearly, from 11 to 22%. Very, very famous results. So crazy somehow. Yeah? You explained it like a human. And then this was even better when you literally could just ask the model to think before it gives you an answer. Like in my interview process, I'm asking my interviewers, think before you give an answer. It's basically the same thing, because in its database, it has some examples of sorting, right? So obviously, it knows all of these things. It knows all of the algorithms that it needs to apply. You just need to tell it, think about it first. Please don't give me an immediate answer. Like many of our children, we teach them, our students. Then this was generalized to a multiple chain of thought, basically self-consistency, a tree of thought where you could reuse thoughts. And one of our contributions here was graph of thoughts. And this is an obvious contribution. It was led by Amache Vesta, one of my senior scientists, was an obvious contribution because in some sense, when we prove theorems, we very often have theorem 1 and theorem 2, and then we derive theorem 3 or corollary 1 or whatever. We combine thoughts. And this is really what this means, because in a tree of thought, you couldn't combine thoughts, obviously, because it's a tree, right? So now the question is, how do we get to those thoughts, though? I had endless discussions with my students. What is even a thought in this formulation? It's a set of tokens. It's somehow something that a model spits out and then ingests again to make a next step. But it's really hard to define what a thought actually is. But now I want to go 10 years back. 10 years back, what actually happened is also a very interesting step in humanity, as we all know. And David Silver is probably still here. So the 18 times world champion in Go, a game that is trivial to explain to anybody. The rules really require nearly no knowledge whatsoever, but it's extremely hard to play. You need a lot of, at least against top players, okay? You need a lot of reasoning to win in that game. So this is a very nice example of human reasoning, extreme human reasoning in some sense. And the 18 times world champion has been beaten by a machine 10 years ago. So how did we do it? Or how did the team do it? I wasn't involved. But it's a very simple reinforcement learning process. So you model the board as a state, then you ask your policy function to give you a next move, but actually you sample m next moves, so you ask the policy function m times, that's great. Then you ask a value function, how likely is the new state resulting from those moves to lead you to a winning game? And then obviously you do a greedy strategy on the value function because if you're not stupid, you pick the likeliest to win. You keep expanding this, you keep doing this again, you may backtrack sometimes, and so on and so on. That's basically it. The big breakthrough at the time was that the policy function was a neural network, a deep neural network. The value function was also a deep neural network. Actually, by today's standards, they weren't even deep. So they were actually pretty small neural networks. And this is why it didn't require a lot of compute at the time to do this. I mean, it required a lot, but not supercomputing level, not Jack Dongarra style compute. So 1,600 expansions, it worked really well, and this is it. And now the question is, how do we apply this to the thoughts? So the idea is very, very simple. We basically have the thoughts as a state. So this is our initial state, this is my question, sort these numbers. Then I ask my policy function, which is now a deep neural network, to generate the next step in my reasoning chain, right? So let's do this. And it may output kind of stupid things like numbers are blue, but then the value function may fix it, right? So we keep doing the same method actually over and over again. And so this is all well known at this point, but what is the difference? The difference is, and I mentioned I'm a performance guy, the difference is that now the policy function and the value function are actually deep neural networks. And did I mention that they're extremely expensive to run? Now every single step may cost me significant resources in terms of CO2 emission, in terms of chips, in terms of money, in terms of human effort. So this is a huge problem, and I believe this is somewhat nice, but it has this problem of performance. So now, what does this mean? Now looking forward, if we take together the superhuman strategy play together with the superhuman knowledge, it seems kind of obvious that this will create a superhuman reasoning system if we had the compute. So this is still an open question, so this is not solved, but we are pretty close. But what we really need is we need to enable that compute. And that's my motivation to you, to work on faster computers, to work on cheaper systems to some sense. It's not all about money, it's about enabling capabilities today when we have these computers. If I had some more time, we could actually do a quiz where you could beat the best AI in about 5 minutes. So there are some cases where this is relatively easy to understand that we are not done yet. So we have to go forward. And actually, I want to close with a call to action. And this is really the part I'm working on. So I presented other people's work so far to motivate you, because I was trying to spark your mind. How can we advance humanity? How can we go forward? So my research a lot focuses on making these models more performant, cheaper, more sustainable in many ways. Two fundamental techniques there to compress models are sparsification and quantization. So sparsification is a way to reduce the number of parameters somehow. There are many, many techniques, number of parameters or intermediate values or anything like reduce the number of computations we do at the end. Quantization, on the other hand, is we reduce the accuracy or we reduce the complexity of each single computation by reducing the bit width of the operands we are doing. Okay, so these are fundamental methods, but they're unfortunately kind of running out of steam at this point because we have very sparse models. We run highly quantized models. At the end, you're down to 1 bit. I mean, you need 1 bit at least. So there's not too much to do. So now we need to look at other things. So for example, we need cheaper computing. We need to build cheaper systems. And one of those cheaper systems is the Maya system, for example, at Microsoft that we are building. I'm involved in that, the Microsoft AI architecture, but you could also look at GPUs. You could look at completely new architectures like the Cerebras wafer scale engine. And I want to motivate all of us to look into that as well. Like what is the way, how do we build cheaper, more sustainable systems? And the principles, I would say here, are data types, sparsity, and spatial. And spatial has been a little bit underexplored. Spatial means you want to minimize the data movement on chip or in your system to really save energy at the end. And then the last part is really we need cheaper systems to some sense, in some sense, like overall systems. These were chips. But here we need to connect these systems. Because at the end, the cardiovascular system of a computer, of a supercomputer, is the network. This is where the blood flows. This is where the heart beats, in the network. And if the network is messed up, then the computer is not going to run very well. So here we are running an effort that's called Ultra Ethernet to make the good old Ethernet. So we have Bob Metcalfe here. The good old Ethernet run well for AI or support AI and HPC applications. And that's a huge effort. And here the principles are high local bandwidth, reliability, and cost. And with that, I would want to thank you. And there's a full version of this video online in case you're interested. Thank you very much.
Right, so our fourth speaker of the morning, Subhash Khot. We are back doing mathematical genealogy, which you may remember from Monday when I introduced this concept. So Subhash worked under Sanjeev Arora, one of our speakers on Monday. He was a doctoral advisor, which makes Subhash the academic son of Sanjeev. Now, you may remember that Sanjeev also shared an advisor with Madhu Sudan, and so therefore Subhash is the academic nephew of Madhu Sudan. And remember, this is all on the quiz tomorrow. Right. So Subhash was awarded the 2014 Abacus Medal, and this morning we'll be talking on approximability of satisfiable constraint satisfaction problems. Subhash.
Thanks for the introduction. It's great to be here, my first time at HLF. I'm not sure I can offer a spark. Instead, I will offer a theorem. So I'll talk about approximability of constraint satisfaction problems, in particular on satisfiable instances. This is something I'm excited about. We have been doing for the last 5 years with co-authors A.M., Dor, Yang Liu, and Mark Braverman. So CSPs, or constraint satisfaction problems, these are probably the most well-known canonical family of NP-hard problems. So perhaps most famous example is 3-SAT. So here we have an underlying predicate called P. It's a predicate on 3 bits and evaluates to true or false. So you can think of 0 as logical false, 1 as logical true. And the predicate is P of XYZ is X or Y or Z. And the corresponding CSP is the instance of the CSP consists of variables and constraints. You have variables x1 through xn, and the constraints are this predicate P applied to triples of variables. So you could have a constraint on variables 1, 7, and 8, another constraint on variables 9, 3, and 2, and so on and so forth. And the variables could appear in negated form. The instance is called satisfiable if you can assign true-false values to the variables so as to satisfy every constraint, meaning so that every predicate evaluates to true. Another example is 3-lin, where the constraints are linear, let's say linear modulo 2, where the predicate P, again on 3 bits, and it evaluates to true if and only if x plus y plus z is 0 mod 2. And you will again have variables and constraints. And what's the complexity of solving this problem? Meaning, given an instance, you want to decide whether it's satisfiable or not. So it's well known that 3-SAT is NP-hard, whereas 3-lin, it's a system of linear equations mod 2. You can solve it using Gaussian elimination. So this is in P, polynomial time solvable. And we would like to understand what makes 3-SAT hard and 3-lin easy. Is there a general theory about this? How about those which are hard? How about approximating solutions to the CSPs? More generally, you can just, again, restating the definition. So you could have a predicate with underlying alphabet sigma of arity k, and size of the alphabet and the arity k, they are thought of constants, let's say 5. And you have the instance of CSPs, variables, and constraints. And the satisfiability question is, I give an instance, I tell you that it's satisfiable. Can you find me an assignment, satisfying assignment in polynomial time? As we saw, it can either be NP-hard, such as 3-SAT. Another NP-hard example would be graph 3 coloring. You want to assign one of 3 colors to the vertices of a graph. And the constraints are on edges, that for every edge, the colors have to be distinct. That's NP-hard. Or the problem can be polynomial time solvable, such as 3-lin that I just mentioned. You could also take graph 2 coloring. That happens to be in P. You could also take 2-SAT. That's also in P. And when is NP-hard? When it's in P, can it have intermediate complexity, something between P and NP-hard? And in principle, it's possible. If P is not equal to NP, it's known that there are computational problems which have intermediate complexity. But turns out, we know by now that for CSPs, there is a strict dichotomy. All CSPs are either in P or NP-hard. Though it was actually a great achievement to get to this point, to prove this referred to as dichotomy theorem. This was proved as early as 78. That's when I was born. By Schaefer, that he showed that if the alphabet is Boolean, then for all predicates of all arities, it's either in P or it's NP-hard. And this was conjectured that the same dichotomy holds for all CSPs over all finite size alphabets and arities. And this has been studied through what's referred to as the algebraic point of view, algebraic methods. And there is an analytical approach which is also proposed. I would be happy if the analytical approach also succeeds, but not so far. And by now, we know this. This was done only fairly recently. Following a long line of work, Zook and Buloto, they did show that all CSPs are either in P or NP-hard. And moreover, there is a very nice characterization of those which are in P and those which are NP-hard. And moreover, those which are in P, the algorithm to solve these is some combination of Gaussian elimination over abelian groups and linear programming relaxations. And the characterization is quite nice. It says that the CSP is in P if and only if it has what is known as a polymorphism. So I will tell you what a polymorphism is. And maybe if you just want to take one nice tidbit from this talk, this would be it. What's a polymorphism? It can be viewed as a solution mixer, meaning it's a method to combine solutions or satisfying assignments to CSP and generate new satisfying assignments. So how does this work? So suppose I have a predicate P, right, of arity K. And a polymorphism is a function, I will say how it works, which take any, let's say, 100 satisfying assignments. So it's arity K, so the rows represent satisfying assignments to this predicate. Now, if there is a function which you can apply to the columns of this matrix, so let's say the alphabet is sigma, and it's a function from sigma to the 100 to sigma. So you can apply it to each column, and you will get another row, right? Apply the function to each column. And if it's the case that if all 100 rows are satisfying assignments, then the output is also a satisfying assignment. Then such a function is called a polymorphism. And the characterization is that the CSP is polynomial time solvable if and only if there exists a non-trivial polymorphism. So just as a quick example, let's say 2-SAT. We know that 2-SAT is in P. So according to this characterization, there ought to be a polymorphism. And here is a polymorphism for 2-SAT. So 2-SAT corresponds to the predicate X or Y. So my polymorphism is simply the majority function. And why is it a polymorphism? Write down any, let's say M is, it can really be anything, but maybe an odd integer. So write down any M satisfying assignments to 2-SAT. So satisfying assignments has to satisfy X or Y. So you will see that in each row, at least one of the bits has to be 1. So if you write down M rows such that in each row, at least one of the bit is 1, then you can apply a majority function to each column, and then you are guaranteed that the 2 bits that you get up by applying majority, there will also be 1. And hence, the majority function is the polymorphism for 2-SAT. And even though we know, different algorithms to solve 2-SAT, there is an algorithm which uses the polymorphism. It's a quite nice algorithm. Yeah, that's just the definition of polymorphism. So this, this is the dichotomy conjecture theorem and the characterization of those polynomial time-solvable cases. So how about approximation? And this is the question we started studying, that those CSPs which are NP-hard, can you solve them approximately? And here is a conjecture that you could make, that for every CSP which is NP-hard, maybe there is a threshold called alpha, such that that's a tight approximation threshold, meaning there is a polynomial time algorithm which, for every satisfiable instance of the CSP, finds an assignment which satisfies alpha fraction of the constraints as opposed to all constraints. And that's the notion of the approximation. I want to satisfy some large alpha fraction of the constraints. But moreover, doing even slightly better than alpha is NP-hard, right? So in that case, alpha is a tight threshold, threshold for hardness. Our current state of knowledge actually suggests quite strongly that this conjecture should be true, that such thresholds should exist. So in particular, for example, for 3-SAT, it's a very well-known celebrated result by Hastad, which actually shows that the threshold is 7/8. Meaning for 3-SAT, on a satisfiable instance, of course, I can find 7/8 satisfying assignment just by taking an assignment uniformly at random. Hastad showed that it's NP-hard to do better than 7/8. And proving this conjecture, it looks quite challenging. You will have to consider what the potential algorithms are. These could be some combinations of linear programming and Gaussian elimination over abelian groups. But also it could be what's known as the semi-definite programming relaxations, and maybe somehow combine all of these together. This we view as a long-term project, which would have to combine all the challenges from all the existing works, including the dichotomy theorem itself. There is the work of Raghavendra, which actually solves this problem on near satisfiable instances versus satisfiable instances, as opposed to satisfiable instances. It turns out even pretty serious questions in extremal combinatorics and what are known as Gowers uniformity norms. We'll have to answer these questions as well. So this is ongoing work. We did produce a fair number of new results across algorithms, computational complexity, and combinatorics. So I will just quickly state one theorem that I promised in combinatorics, since this is also joint with math, and then I will end. So this is a result called density Hell's-Jewett theorem. So it's a Ramsey type result. So you know that in Ramsey area, you want to show that any large enough combinatorial structure contains a very specific substructure. So it's a theorem of that kind. It's about combinatorial lines. So consider a hypercube with n dimensions over alphabet of size k. So the alphabet is referred to as 0, 1 up to k minus 1. And a combinatorial line in this space is a set of k points called x0 up to x sub k minus 1, such that on every coordinate, if you look at the sequence of k points, on every coordinate, they're either equal or they are 0, 1, 2 up to k minus 1 in that specific order. Okay? So just an example, for k equals 3 and the dimension being 4, these 3 points, they form a combinatorial line. There are 4 coordinates, and you can see that on the red coordinates, it's either 1, 1, 1, 2, 2, 2. And on the green coordinates, it's 0, 1, 2 in that order. So that's a combinatorial line in k equals 3. It turns out that the combinatorial line is also very actually specific type of k-term arithmetic progression. And this also suggests that somehow this problem is more general than problem of finding arithmetic progressions. And that's in some sense actually the beauty of this problem, that it captures the essence of many, many problems. And the question is, if you have a subset of the hypercube, which has guaranteed that it has no combinatorial lines, then can you prove an upper bound on the size of any such subset? How dense can it be? And as I said, this actually governs or leads to upper bounds on many, many other problems in additive combinatorics and also in computational complexity, such as the parallel repetition theorems, in particular, Zemedi's theorems on arithmetic progressions. And somehow, surprisingly, even showing that as n tends to infinity, there is an upper bound on these combinatorial line-free sets, and that the upper bound tends to 0 as n tends to infinity. Even this somehow was surprisingly difficult, and this was done in Furstenberg and Kaz-Nelson in early 90s. And their proof uses ergodic theory, and it did not give any quantitative explicit upper bounds. And this was obtained in about 2010. And this was the first polymath project. This was the idea that large teams of mathematicians would work together on a problem in open discussions, right? And in this project, they did obtain upper bound on the density of such sets. For k equals 3, it was something like 1 over square root of log star n, which is a very weak bound. And for larger k, it's even weaker. And somehow we managed to obtain upper bound, which is still weak. It's 1 over something like 4 logs of n. But in this business, even this bound actually qualifies as a reasonable bound. Any case, and what's nice for us was we came from computer science motivation, trying to study approximability of constraint satisfaction problems, and after 5 years and many hundreds of pages in some roundabout way, hit upon something which actually was some central problem in combinatorics, and then that's it. Thank you.
So that brings us to our final speaker of this morning's session and our final Sparks speaker of the week, which will be Leslie Lamport. Now, we, of course, opened this morning with that wonderful poem from Joshua, but it's not the first time that we've had poetry on the stage at the HLF. As those of us who were here last year, fortunate enough to be here last year, will remember during the lightning talks, Leslie actually treated us to a 3¼ minute performance of his publication, The Byzantine Generals. So I have high hopes of what we might see today. Leslie was awarded the 2013 Turing Award. Today we'll be talking on why programs should have bugs. Leslie.
Thank you. Okay. Why programs should have bugs. I began writing programs in 1957. And we can write much more complex programs today than we did then. And one reason is that programming languages have improved. But the main reason is that there are libraries of subprograms that we can use. These subprograms are no different than other programs. So I'm going to drop the sub and just call them programs as well. Most programs have no bugs because they can't. They should be able to. But to have a bug, a program must have a description of exactly what it should do. And most programs have no description. Or if they have a description, they're not precise enough to tell what it should do. The hardest part of programming is figuring out what the subprograms we use do. This now can require hours of experimentation, or reading 1,000 lines of codes, which is generally uncommented because real programmers don't write comments. A description of what a program does should be written before any code. We want our programs to be easy to use. And the only way to know how easy a program will be to use, first by somebody else, is to write a precise description of how that other person should use it. Now, I found another reason to decide what a program should do before writing any code. Doing it often reveals that my initial idea of what I wanted to do would require too much work to implement it, and I'm pretty lazy. And this generally leads me to write a different program that would be good enough to work, good enough for what I needed, and a lot less work. So why don't most programmers write precise descriptions of what their programs do? Well, there are two reasons. Reason one is, even if they try, they don't know how. The World Wide Web Consortium, W3C, they're the people that specify subprograms, they call them methods, that other programs can use to implement web page features. And these are smart people, they're experts, they actually tried. And they describe every subprogram by specifying the results it produces as a function of its arguments. If the for example, if the subprogram sets the values of two registers, X and Y, then they specify the new values of X and Y as functions of the input and the current values of X and Y. What they fail to specify is the order in which the values of X and Y are changed. Well, why does the order matter? Well, I wrote a video course a few years ago meant to be viewed on the web. And the web program I wrote to display the videos is a concurrent program. Why is it a concurrent program? Well, for example, there's a subprogram that handles a mouse click. And there's another subprogram that could be running at the same time that is executed when the video reaches a certain point. And those two subprograms can be running simultaneously, concurrently. And the order in which a subprogram sets the value of X and Y matters if another subprogram running at the same time is reading those values. And the hard part of writing my program was figuring out the order in which the subprograms could perform their actions. And the order wasn't specified by the W3C specification, so it could differ on different browsers or even on different executions of the same browser. And I wasn't about to read thousands of lines of code of all the different browsers. So that required a lot of experimentation. And I haven't learned of any bugs in that particular aspect of my program. But any new release of a browser could introduce a bug. So why don't programmers write precise descriptions of what their programs do? Reason two, a description of what a program does should be understandable by the user. But most programmers seem to be better at communicating with computers than with other people. And so the result of this is agile programming. Have you heard of agile programming? Well, agile programming, it's two steps. First, you write any program you like, and then you keep modifying it until the user stops complaining. And that's agile programming. Okay, thank you.
Leslie, thank you. Do you want to try a question or two? Yeah, I mean, we have time, and I promise that this would then complete the set of having at least one question in each Spark session. So does anyone have a question or two for Leslie? We do have the time for it, so why not try? I can see a hand over there in a dashing turquoise outfit. There is a microphone coming. I think it might be thrown, so watch out. There we go. Inaccurately thrown. Okay.
Hi, Leslie. Great talk. I was just curious on how you think the description could maybe be standardized to be parsed by other program readers, and if you think that's a valiant effort at all to maybe standardize how programs work in that matter. if we can create like a description language to standardize how the subprograms can understand like the code, if that makes sense.
Programmers are too hung up on language. I'm not interested in languages. I'm interested in what those languages are trying to express. And so if you want to know, the question is, how should you explain what these programs should do? Well, for particular class of programs, which are concurrent system programs, I have a book that is going to be published in March, and you can read that. It'll tell you in 300 pages how to do it. I'm not going to try to explain that now.
There you go. Answer in the book. And then we just got one other hand, a couple of rows forwards. There we go.
Great talk. So did you consider how AI could help us? Could generative AI generate the specification on the one hand, and on the other hand is vibe coding, where the people vaguely express what they want to do and the AI generates something on the path to a solution, or is it a horrible thing and we're all doomed?
Well, my experience seems to indicate that AI programs learn how to program by reading what goes on in the web. And so all of these programs that they're using as examples are written by people who don't know how to specify how the program should be written. So your AI program. I mean, one example of that is that, and for a little talk I gave, I showed a little program about 6 lines long. And this was through a conference of Unix programmers. And I said, does anybody see the error in this program? And out of about 300 people, one of them raised their hand. Well, I gave that same problem to ChatGPT and said, write a program that does this. And it produced exactly the same bug.
In the interest of time, we will leave it there. So again, Leslie, thank you. And thank you for taking questions. I did pose a question to you all on Tuesday morning in the Spark session about patterns you might be able to identify in the laureates that have multiple awards, as there are 10 of them in total, some of them, of course, attending this week. So does anyone think they spotted what those patterns might be? No one feeling brave? Or did everyone forget? Everyone just forgot that I asked this as a question, didn't they? Well, I thought there were 2. I identified there were 2 patterns. So I think one of them is fairly, I wouldn't say obvious, but it makes sense. It's the laureates, of course, who work cross-disciplinarily. So in maths and computer science, of course, then it makes sense if you do groundbreaking work and you're working in both areas, you could expect to receive awards from both subjects. And I also noticed an interesting pattern of the laureates who received a prize very early in their career would then often receive a prize towards the end of their career. So kind of the older you are, the more likely you are to have multiple awards was the other pattern that I identified. And with that, I will finish for today.